And mechanisms are actually important because, well, first of all, kinetics is an important topic because it not only allows you to figure out the speed of the reaction, but through detailed experiments, you can actually figure out the mechanism. And why is the mechanism important? Because it's really the key as to what chemicals are responsible and under what conditions can you optimize this reaction, or maybe you don't want the reaction to go. So figure out a way to hinder that reaction. So make sure that you are able to, at least in this part, get an overview of how we can use the mechanism of the reaction via kinetics to figure out the rate law, okay? Usually what happens is you figure out the rate law based on experiments that we've covered already in the previous sections of this chapter, and then you draw up a mechanism that is consistent with that rate law. If you are going to be a pharmaceutical scientist, if you're going to be someone who goes on to organic chemistry, mechanism is a big role in terms of understanding how these chemicals interact at an intimate level in order to get the reactions to go. So let's go ahead and start here. And what you see in this slide right here is actually, it's over here, is actually an illustration from the stratosphere, because how we learn about the ozone layer depletion was based on kinetics. And what happened was we studied what chemicals were in the stratosphere to figure out why we had such a depletion on the ozone. And for those of you who don't know, remember that the ozone is a layer in the stratosphere in which you have O3. And the reason why that chemical is important is because it's basically the sun blocker. It's like the sunscreen for planet Earth. When that layer is thinned out or non-existent, then all the UV radiation hits the surface of the planet. And of course, anything lower than about maybe 380 nanometers, even 400 nanometers, if it make contact with our skin, will cause damage to our DNA, and damage to our DNA causes mutation, and mutation can cause cancer. So anyway, let's continue with this right here. Here you see the layers in our atmosphere. The stratosphere is the layer directly above us, okay? And the layer, and it covers a little bit above Mount Everest. Mount Everest, about 36,000 feet elevation. And the next layer above that is the stratosphere. And in the stratosphere, what you see is the ozone layer right here. Ozone, of course, is O3. It's a chemical that is bent like that. And the reason why it's important is because when radiation hits it, it cleaves that bond, but more importantly, it absorbs that radiation, and it prevents that radiation from going further down the stratosphere, okay? So here's how, this is called the Chapman cycle, and this is how the ozone layer works to protect the planet. You have oxygen, and you know that oxygen is pretty much common in our atmosphere. The higher we go, of course, the less molecules of gas that we have, and therefore the amount of oxygen is lowered. It doesn't mean that the percent of oxygen is lower, it just means that the amount of oxygen gas, or the amount of gas particle, is lowered, and therefore the amount moles of oxygen is also lowered. That's why if you are an athlete and you play in Denver versus San Diego, what happens a lot is that you have a shortness of breath just because there's less oxygen available, less air available in general. So what happens is in the stratosphere, you still have oxygen, and you also have an accumulation of ozone, because ozone likes to go there, and they tend to hover there, okay? But what happens is that 242 nanometers radiation, and that's all already at the ultraviolet level. When it makes contact with our atmosphere, it gets absorbed by the oxygen, and it cleaves the oxygen molecule to two oxygen atoms. Well, those oxygen atoms can now collide with an oxygen molecule here, and what you get is ozone, O3. So that reaction is important because that's the ozone creation pathway. That is, ozone is created. Um, then the important thing about that particular chemical is that 320 nanometers or less. Remember that oxygen, O2, filters out 242, but 320 nanometers, that's still in the UV region. And we call it the near UV because it's closest to the visible spectrum. The visible spectrum is about maybe 800 nanometers to about 480 nanometers. And then once you get below 480, you get to the ultraviolet. So you can see that 320 is way into the ultraviolet here, but the 320 nanometers or less, those are the radiation that has high enough energy that it cleaves the ozone bond and breaks it up. So what you have is this chemical breaking apart right here, and you get an ozone, an oxygen coming out, and you get a regeneration of O2. Anyway, this cycle keeps on going, and that's how we get ozone sustained in our stratosphere. But anything that causes this reaction to not go back to its original, okay, that depletes ozone right here, is going to be a chain terminating step. And you don't really want to do that because you need the ozone there as a filter. So this is a movie and sort of shows that. You guys can watch it, but it basically shows, yeah, clear this real quick, that the ozone is in the stratosphere here. And let me see if I can't, the video, because it's playing through my iPad, is not producing the sound, but you can still see here that a reaction occurs in which we have both ozone being formed. Anyway, you guys can watch that if you go to the main PowerPoint or the PowerPoint slide. Let me go ahead and get out of that. But this is the reaction right here. A key reaction in the upper atmosphere is the terminating step, in which ozone reacts with an oxygen atom to produce oxygen molecule. And that actually only has a activation barrier of 19 kilojoules. 19 kilojoules isn't very much, but it still has an activation barrier, okay, an activation energy barrier. But that right there is the reaction coordinate diagram for this particular reaction that you see. And then the delta H of reaction. Remember, the delta H of the reaction is how much energy do you have of the reactant, how much energy do you have of the product. And so that difference right here is a delta H reaction, and that's negative 392. This means that it's an exothermic reaction, okay? This is an exothermic reaction, and the oxygen molecules are much more stable than the ozone and the oxygen atom. So let's go ahead and move on. What are the other ways of ozone destruction? Well, water actually contributes to the ozone destruction. And these are the different mechanisms by which these chemicals will remove ozone from our stratosphere. And you might say, well, water is a plentiful molecule. And so what should we do? Should we prevent that? No, it just so happens. There are certain chemical reactions that will just naturally occur. The key is not to prevent the naturally occurring reaction from occurring. The key is to prevent man-made reaction from occurring. Just like we have climate, global warming these days. Well, the global warming, the warming and the cooling of our planet Earth is actually a recurring cycle that happens every 20,000 years. But because of the Industrial Revolution, we've actually accelerated the global warming process by the fact that we've been burning all these hydrocarbons and then causing the carbon dioxide um, molecules to be produced into our atmosphere. And that has caused this global warming um, crisis that we have now. And that's why California is burning down. That's why within the past 5 years, we've seen the warmest temperature in this planet ever recorded. Okay, so keep that in mind. It's the carbon dioxide um, concentration, and we measure carbon dioxide concentration in parts per million. It's the carbon dioxide concentration that is accumulating due to the Industrial Revolution. And so what we need to do is we need to find solutions to kind of reduce that, or even find solutions where we can eat up carbon dioxide in our atmosphere. But that's a really tough problem to solve, because we've taken decades and decades and decades of producing carbon dioxide. We don't have decades to remove the carbon dioxide. We're going to be in a big crisis. Anyway, let's go back here. Sometimes I just go off in a tangent. But here you can see that water will break up to hydroxide and hydrogen. These are called radicals. Radicals are uh, chemicals with an unpaired electron. Okay, so because they have an unpaired electrons, they're very reactive. And what they need to do is they need to find another electron to make that more stable. And so what happens here is that the hydrogen I radical will react with ozone and produce a hydroxide and oxygen molecule. But see, what's happening here is that the ozone is being depleted by this reaction. And then the hydroxide ions that are produced can react with oxygen atom to produce, again, hydrogen radicals and then O2 molecules. But this now will go back and attack another ozone molecule. So that cycle keeps repeating itself until you get to a chain terminating step. Maybe two hydrogen radicals combined together. And this is not the likely case because those are going to be low in concentration versus ozone, but two hydrogen radicals come together and you can produce hydrogen gas. Okay, but that's a reaction mechanism that is proposed in terms of how water depletes ozone. Nitrogen, 78% in our atmosphere, also can deplete ozone, in which here you have nitrogen plus oxygen produce 2NO. Then the NO reacts with ozone to produce NO2 and oxygen. Again, any reaction that reacts with O3 and removes that is going to be harmful. But of course, this is a reaction that is part of nature. Okay, this reaction, however, is not a part of nature. This reaction is why chlorofluorocarbon was banned from hairspray and aerosol cans. It's why chlorofluorocarbons in air conditioner refrigerants and refrigerators is so closely monitored, because what they discovered was that when this thing goes into, and what makes chlorofluorocarbon an important chemical and a robust chemical here in planet Earth is also the reason why it's dangerous up in the stratosphere. Here in planet Earth, we like chlorofluorocarbon because it doesn't react with anything. It's inert, okay? So we spill it, it's not gonna contaminate our atmosphere, because what will happen is it'll turn to a gas and then it'll basically just vaporize somewhere. But where does it go? It goes up into our stratosphere. And in our stratosphere, this is the reaction. The chlorofluorocarbon, sorry, this should be over to the left, okay? Actually, take that back. This CCl2F2, the reason why it's called a chlorofluorocarbon is because it's got chlorine and fluorine. and carbon. That's why it's called chlorofluorocarbon. Okay, this thing will cleave a chlorine, and you get these two radicals, a chlorine radical and a fragment from that chlorofluorocarbon. Anyway, these chemicals right here, the chlorine especially, will react with ozone, and again, it ties up the ozone. So it just so happens that for every this reaction right here can take down about 10,000 ozone, O3, for every one chlorofluorocarbon. So you can see that these chemicals really here are catalysts. They catalyze the breakdown of ozone. So let's take a look at our reaction again. The reaction that I want to speak out is this right here. Okay, this is the reaction that I'm talking about. And I'm going to show you that again here. This right here is 19 kilojoules. But look what happens when you introduce chlorofluorocarbons and the chlorine radicals come in to catalyze the reaction. You go from 19 kilojoules to something like this, which is very, very small relative to the original reaction. That's why the reaction, that's why we say chlorofluorocarbons are catalysts, because it lowers the activation energy of this reaction via a different pathway, a different reaction mechanism. So you can watch this movie again. The movie just kind of shows you how chlorofluorocarbon reacts at the intimate level and breaks down the ozone. Okay, and all this is based on the kinetic study that was done. In fact, the person, Morina, I believe, is a professor. He used to be a professor back east. He won the Nobel Prize for making this discovery. And then UC Irvine actually recruited him in the 1990s, and he's a professor now at UC Irvine. But he's responsible for trying to figure out exactly why we had this ozone depletion back in the 80s and 90s. Here's what you need to know about reaction mechanism. In reaction mechanism, the individual steps by which the molecules combine are called the elementary steps. When you add up the elementary step, you have the overall stoichiometry. Okay, so the mechanism of a reaction is a sequence of steps at the molecular level that shows how the reactant chemicals combine to form the products and even the intermediates. And so these multi-step reactions are the elementary steps. The stoichiometry is when you add up all the elementary steps and then you cancel the intermediates in the reaction. So what you have is the overall stoichiometry. And what is important is because we can get a lot from the rate law, and from the rate law we can propose a mechanism. If the mechanism is consistent with the rate law, then we can say that's a plausible mechanism for this reaction. Okay, we can't say for sure that it's the mechanism for this reaction, but we can say it's a plausible mechanism for the reaction because it's consistent with the rate law. So let's go ahead and take a look at the Chapman cycle. These are the elementary steps. It's a two-step mechanism. Okay, and again, when this is step one, this is step two, and then when to get your overall stoichiometry, you just add the two. You see there's an O3 here, but this oxygen and this oxygen cancels, and so it's not going to be written in the overall stoichiometry. And what you have is you have 2 O3 and you've got 3 O2. So that's your overall stoichiometry, okay? The intermediates in the reaction will cancel and do not show up in the overall stoichiometry, okay? So in general, if you have any, say, reaction, and let's say this is the slow step. The slow step is also called the rate determining step. because the slow step in the reaction mechanism determines how fast that reaction is going to go. And I'll explain to you how we recognize that. So if we know that that's a slow step in the reaction, then we can write a rate law based on that slow step. And we can say that the rate is equal to the chemical A taken to the I power and the chemical B taken to the J power, where if we know the balance equation for that slow step, then we can write the rate law for that reaction. Okay. So the rate law of the reaction is directly proportional to the concentrations of the colliding species based on the slow step, not on the overall stoichiometry. Okay, it's based on the slow step of the reaction mechanism. Remember, this is the overall stoichiometry, and these are the mechanism, and depending on which is the slow step, you can write a rate law from that slow step. Okay. So let's take a look at this right here. This is another reaction mechanism, and this was the reaction mechanism in which NO2 starts to deplete ozone. And this is the slow step. If we want to write the overall stoichiometry, that's easy. What we do is we recognize NO3, make sure that each reaction, each elementary step is balanced in the first place, okay? Whenever I give you a reaction, never assume it's balanced. It's up to you to figure out whether it's balanced or not. And usually it's just quick cursory check to make sure all the atoms are the same. So let me go ahead and show you that we've got one nitrogen here, one nitrogen here. We've got 5 oxygens here, 5 oxygens here. So that's balanced. 2 nitrogens here, 2 nitrogens here. We've got 5 oxygens here, 5 oxygens here. And so what we have is that second reaction, that second elementary step is also balanced. Now, what I want to do is write the overall stoichiometry. I notice that the NO3 are going to cancel. What we have is 2 NO2 plus an O3, and it's going to N2O5 plus O2. That's your overall stoichiometry. Don't make it harder than it is, okay? It's basically just adding up the two reactions and canceling any products that also shows up in your reactant, assuming, of course, that they're the same in quantity. For example, if I have 2 here and I've got 1 there, then it's not going to cancel. What you end up with is 1 extra NO3 in this side, okay? So again, just make sure that each elementary step is balanced, and then you can do your overall stoichiometry. So it looks like that's good. Because this is the slow step, then I can just write the rate law directly. The rate law is equal to the rate. Remember, the rate is how fast a reaction is going. It's going to be in, say, molarity per second, or molarity per minute, or molarity per time. And that is equal to a rate constant K. And remember that you can determine K from the Arrhenius equation. Embedded in K is the orientation and the sterics and the activation energy. And then the chemical, remember these are what you guys figured out in the methods of initial rate. Well, this is a different way of figuring out the rate law rather than the method of initial rate. What we have here is the chemicals NO2, because that's the first step. And then there's a 1 right here, and there's a 1 right there as well. So that's the first power. And then we have O3, and that's also to the first power. Okay. What do the slow tells you that that reaction is slow relative to the other ones. And I'll explain that shortly, okay? I'll make sure that you understand that, because these reaction has a certain amount of speed, and remember that the rate of the reaction is actually related to its activation energy. You see how all that comes together in the next few slides, okay? But this is the rate law. Pretty easy, because the first reaction is the slow step. Okay, the first reaction or the first elementary step is the slow step. Okay, so that's basically what we have here. Let me just make sure that everything's okay. I'm looking at my chat here. Uh, okay, most of it is the most was the last question was trying to define what slow and fast means. Okay, and I'll explain that shortly here. Okay, so let me go ahead and clear this. In a series of steps, the slowest elementary step, that is the rate determining step, and that determines the speed of the reaction overall. Okay, so let's take a look at molecularity first, and then we'll go back to the rate determining step. Elementary step, whenever you have, say, some chemical to the first power, first order, then we say it's first order and it's unimolecular. Okay, when something's to the first order, then it's unimolecular. And this might be a first order kinetics reaction. Suppose we have a second order kinetic reaction. Second order kinetic reaction is the rate is equal to K times the reactant squared. So this squared right here tells you it's second order and it's bimolecular. Now let's say that it's two different chemicals, two different reactants combining. Well, A to the first plus B times B to the first, 1 plus 1 equals 2. So that's also a bimolecular reaction. What we say is that it's first order in A, first order in B, but second order overall. Okay, the overall is the sum of the superscript in the rate law. So it's first order in A, first order in B, and second order overall. Okay, so let's take a look at the next plausible molecularity in terms of the elementary step. And we're not really going to go higher than this because term molecular, three chemicals combining at the same time, is actually a rare incident. It does happen because we have moles and moles of chemicals, but it's rare. And so if you're going to propose a term molecular mechanism, you better have good evidence. You could imagine a quad molecular molecularity. That's even more rare, and it probably doesn't happen except for once in a blue moon. But this is a term molecular. What we have here is we've got A, three chemicals of reactant, all same reactant colliding all at once. You have maybe two A's and one B, so 2 plus 1 equals 3. Or we have A plus B plus C equals 3. So in this right here, we say it's third order term molecular, third order overall. Here we can say that it's second order in A, first order in B, term molecular, or third order overall. And then here we can say it's first order in A, first order in B, first order in C, again, third order overall. When we say overall, it's basically the sum of the superscript or the order of each individual chemical that is responsible for that reaction. If it's 0, we don't count it. We don't say, you know, it's not counted. If it's 0 plus 1, if it's not involved in, if it's a 0th order reaction, then we say it's 0th order, but there is no molecularity in terms of that. Okay, so let me go ahead and clear this. Term molecular mechanism, third elementary step is a very rare. That is three chemicals combining is very rare. Scientists, again, who propose this got to be very careful with their measurements. Okay, make sure I got everything here. So in a multi-step reaction, most reaction involves more than one elementary step. Some reactions does have one elementary step, and it'll look like this. Okay, it's got one hump. It's going from A to B products, reactant to products, and it's got one activation barrier. In a two-step mechanism, what you have is you've got two activation barrier. This is reactant going to the intermediate, intermediate going to product. So this is the reaction that you will see. The overall stoichiometry is reactant going to product. Notice that in a two-step mechanism, you've got two humps, two activation barriers, okay, and one intermediate. In a three-step reaction mechanism, you're going to have three humps, okay? This is the first reaction, this is the second reaction, and this is the third reaction. So you can actually figure out how many elementary steps you have in a reaction just based on the number of humps the reaction mechanism have. Remember that the number of intermediate will be, or valleys, will be one lower than the number of steps. So keep that in mind. So rate limiting step is the slowest step. And you can think about this in terms of if you ever drove up to Big Bear, you know that that road is up, has a high incline. And what usually happens is that it's a one lane road for some of the parts, some of the segments there. And if you got a slow car that's going up that hill, then everyone else is going to be slowed down based on the slowest car moving up that hill. Okay, so that's your rate determining step. If no one of these cars are going to bypass the slowest car, then you get there based on the speed of that slowest car. It's like if I was giving an exam and I say that no one can leave until everybody finishes. Well, then you guys are not going to leave until the slowest or the last student completes that exam. Okay, again, the rate determining step, the slowest reaction, the slowest elementary step in that series of reaction is going to determine the speed. Because what will happen is that if you've got reaction 1, reaction 2, reaction 3, if this is the slowest step and all these are fast, then this is your bottleneck right there. If you have reaction 1, reaction 2, reaction 3, and this is your slowest step, then everything will go up to reaction 3 and then be halted. That'll be where your bottleneck will be. So the rate determining step is the reaction, is the reaction that you have to investigate in order to come up with the rate law. Okay, but it's more complicated than that, because your rate law cannot, and let me emphasize this again, your rate law cannot contain intermediates. It's got to have chemical that you can monitor, and the chemicals that you can monitor are the reactants, the catalysts, or maybe the products. Those things you can monitor, but you can't monitor the intermediate. It's very difficult. So if your rate law, if you propose a rate law that has an intermediate in it, then you have to rewrite it so that it contains only those chemicals in your stoichiometry plus maybe a catalyst. Okay, and we will see some examples shortly here as to how we can overcome that. Anyway, I hope this clears up what we mean by slow step and fast step in terms of the overall reactions. Okay, if it's still not clear, then just know that when you have different types of elementary steps, there's always going to be one step that has a very high activation barrier, and that very high activation barrier is your slowest step. Okay, because molecules need to overcome, must have that energy, that very high energy to proceed to the other side. So let's take a look at this right here. This is a reaction in which NO2 and CO and produces NO and carbon dioxide. And again, you can see how we got the overall stoichiometry. What we did in terms of the overall stoichiometry is we canceled NO3. And we can say that the intermediate is equal to NO3 because that's canceled and doesn't show up in the overall stoichiometry. Let's see if we cancel anything else. It looks like everything else is here. So NO3 is our intermediate, and then what we have is an NO2 here and an NO2 here, and then we have an NO2 here, so that also cancels. But it's not really an intermediate because, again, it shows up in the overall stoichiometry, but we still need to cancel out one of the NO2. So we have an NO2, one left over, and a CO, and what we have is an NO and a CO2. It's not difficult to come up with the overall stoichiometry. Okay, if you see a problem like that, consider it easy points. So because I give you a rate law like this, okay, suppose I say, okay, we do this experiment. These are the proposed elementary steps. This is the rate law as found by either looking at the speed or doing the methods of reaction rate. What can you tell me about which is the slow step? Well, if you take a look at this right here, it's second order in NO2. Which of these two elementary steps is that consistent with? Well, this is right here, second NO2 squared. That means that the first step is the rate determining step. Okay, so we can say that this is slow and this is fast. The second reaction is fast, and so we can make that conclusion. Okay, step one is the rate determining step, and that was easy. Okay, that was easy because you didn't really have to do much math in terms of that. Let's see. How is NO2 not an intermediate? Still shows up in the net reaction. Yes, right. It still shows up in the net reaction. Exactly. It's not an intermediate. Only those chemicals that do not show up in the net reaction, because it's produced in one step and then consumed in the other, is an intermediate. Okay, so let's take a look at this right here. This is a reaction with one elementary step. So the profile is going to look like this. It's either an endothermic reaction or exothermic reaction. It depends on the energetics, okay? But it basically has one hump. And because that overall stoichiometry is also an elementary step, remember, if it's one elementary step, then that elementary step is also the overall stoichiometry. That rate law is very simple. Rate is equal to K NO O3. First order in NO, first order in O3, second order overall. That's the vernacular that you guys use for this. This right here, there's two elementary steps. The first step is the slow step. So I can write that rate law as well. Rate is equal to K O3 to the first order in ozone. We don't write anything else because we're not worried about the fast reaction here, because this right here, which is your slow step, determines how fast that reaction goes. Okay, notice that the oxygen is the intermediate, and what we have here is NO plus O3 going to NO2 plus O2. So double check and make sure that your equation is balanced. NO plus O3, that's 4 oxygen on the left, 4 oxygen to the right, and 1 nitrogen in the left and 1 oxygen in the right. So that's a balanced equation. Let me go ahead and clear this real quick because I want to show you something. Because this is the slow step, what happens is that you can draw a rough reaction coordinate diagram for this reaction right here. What you can do is say, okay, the slow step is also going to have the highest transition state. So we can have a reaction that looks like this, like that, okay? And then the next step can look like that. Because this is your highest activation step, that's your slow step. That's your slow step. Okay, you can also draw a reaction coordinate diagram that looks like this. okay? And the reason why this is your slow step is because this transition state is higher energy than this transition step. This is a two-step mechanism. How do I know? I've got two humps right here, okay? But your slow step will always be the step that contains the highest energetic transition state. It doesn't matter that this E Act 2 is larger than this E Act 1, okay? Doesn't matter that that E Act 2 is higher than that E Act 1. The key here is that the molecules need this amount of energy, this energy right here, which is lower than that energy right there. And so that's your rate determining step, okay? That's your rate determining step. And you can see that visually in a reaction coordinate diagram. I hope that sort of makes sense. And you will, hopefully it'll come together when you start working on that activity that I gave you, as well as the lab activity that you have. So let me go ahead and clear this. So the rate here is just K equals NO plus times O3, first order in NO, first order in O3. Here we have the rate is equal to the rate constant K times the O3 to the first power, because this balance equation only has one O3. We don't worry about the second step because the second step is a fast step, okay? So far we've just been working with reactions in which the first step is the slow step. Whenever the first step is a slow step, consider it a gift because you don't have to do much math. But suppose we have a reaction, okay? This is the overall stoichiometry, this is overall stoichiometry. The intermediates are going to cancel, but let's say that we have multiple step mechanism, and then it's not the first step that is rate determining. It's subsequent steps later on. How do we determine the rate law? Remember, I just told you that in the rate law, you cannot have, and I emphasize this again, you cannot have intermediates in your rate law. So even though this is the slow step, I would first start by writing this rate law right here. Rate is equal to K, some K value, times the intermediate. And if this is a balance equation, that's to the first power. But I just told you, you can't write a rate law based on intermediate. So what do we have to do? Well, we have to look at the second reaction right here. Okay, and this second reaction is actually in equilibrium, because what happens is that because you have a bottleneck in the second reaction, the intermediate in that first reaction builds up and then it can reconvert back to A. So that's an equilibrium. Until the second reaction uses up that intermediate, it's not going to proceed any further. That's why we have a double arrow right there. It's being held up, and any accumulation of that intermediate will back react and form the reactant again, A. So until the intermediate starts proceeding in the second step, it's not going to get consumed. Anyway, so when we have a double arrow there, what we have really is an equilibrium. And that equilibrium, okay, will look like this. It'll look like, let's make sure. Oh, I apologize. I should have at least showed you my facial expression, so you can see exactly what I'm talking about in terms of some of these things. Let me do this real quick. Here I am making all these gestures in terms of what to do, and you're just seeing my, hold on, I need to do one thing here. Here. I keep changing this, and then my default setting, and then it always goes back to the original setting. So I apologize for that, okay? Here. Now you can see my facial expression as I kind of explain these things. But I just noticed that you were not seeing some of the gestures that I'm making. Anyway, let me go ahead and finish this real quick. Let's do this. Let's see. Okay. Okay. So let's go back over here and let's take a look at this right here in terms of what's going on. What we have there is the following. We have the slow step being the second step. And when we do that, what we can do is the following here. We can write the mass action expression. And that mass action expression is going to look like this. Okay. A is in equilibrium with the intermediate. So we can say that there's an equilibrium constant KEQ, and KEQ is equal to the ratio of the intermediate taken to the first power, because we only have one there, times A taken to the first power. So that's what we call the mass action expression. And we write that down just based on the fact that it's an equilibrium. How do we know it's an equilibrium? Because we know that it's not the slow step, and we have that double arrow there. So remember, we cannot keep this reaction. This reaction is a no-no. But what we can do is substitute intermediate in here by rearranging this equation. And when I rearrange this equation, I can say that it's equal to K equilibrium times A. Now I can substitute this right here for that. And what I would get is the following. Yeah, clear my screen here. If I do that substitution, what I get is rate is equal to K, and then this has a K equilibrium times A. Okay, so that right there, it substitutes for that. But a K equilibrium is just a rate constant. K is just a rate constant for in terms of the kinetics. K equilibrium is a rate constant in terms of equilibrium. So I can put these two together and say it's K prime. A constant times a constant is just another constant, in other words. So it's okay to lump it all in terms of K. And so what we have now is this. So this would be the official rate law. It's equal to rate times K prime times A. And what we have here now is a rate law that doesn't contain the intermediate, but is expressed based on the first elementary step, which is an equilibrium. Okay, so hopefully that makes sense. When you have problems like that, it becomes a mathematical equation. So let me go ahead and move on to the next page. Okay, yeah, clear this up real quick. So we have that, okay, like I said, and this is the math. This is the math that I just worked out for you. Okay, remember that this right here is based on K equilibrium. It's based on A in equilibrium with intermediate. That's the first step. And what we do is we solve for the intermediate, because that's the parameter that is in our rate law, and we need to remove that. So this is our finished reaction right there. Okay, so let's go to another example right here. We have two reaction mechanisms. This one's easy. The first one's a slow step. It's a no-brainer. The rate is equal to K times NO2 times O3. That's it. Here, what you can say is that the NO3 are the intermediates, the NO2 are the reactants, and O3 is the reactant, N2O5 is a product, O2 is a product. This is the rate law right there. This one right here is a little bit more tricky. You've got a slow step on the second step. So that's where you start. You always write the rate law based on the slow step. So I would say rate is equal to K N2O4 times O3. Let's double check to make sure that the equation is balanced. We have NO2, NO2, N2O4. N2O4 is an intermediate. We get N2O5 and O2. Okay, so the overall stoichiometry is that right there. So what we have here is N2O4. N2O4 is not allowed to be in the rate law. So what we need to do is we need to look at this first reaction and say K equilibrium in that first reaction is products. It's always the products taken to its coefficient over reactant taken to its coefficient. And so this is N2O4, even though it's an intermediate, it's a product in that first step taken to the first power over NO2 squared, because there's two NO2. What we want to do is rearrange this equation for N2O4. K equilibrium times NO2 squared. And then we substitute this whole thing for N2O4. Okay? And we get our finished reaction rate is equal to K. And then O3 is still there. And then we substitute this portion right here, K equilibrium, NO2 squared. And this, again, it's just a math, is K equilibrium, O3, NO2 squared. So what we have by making that second step, the slow step, is a ternary reaction mechanism. First order in ozone, second order in O2, and then make sure that this is just K prime. Okay, make sure that that's just K prime. So let me just show you how that's worked out here. I'm going to clear this. Here's the net result. And then the second one's pretty easy. Okay, it's nothing more than algebra. These chemicals right here are variables, and you just treat them as variables. You treat them like X, Y, or Z when you do algebra. Here's another example, and this is the slow step. This is too easy. Okay, the rate law is going to be rate. Well, let's come up with our overall stoichiometry. Double check to make sure that each reaction is balanced. And two hydrogens, two oxygens, two oxygens, one iodine. That first reaction is balanced. Two hydrogens, three oxygens, one iodine. That second reaction is balanced. So the rate law, again, this is a no-brainer, is going to be equal to K H2O2 I minus. Okay, if you want to make sure that none of these are intermediate, let's take a look right here. We can see that IO minus is an intermediate. That's the only thing that is common to both sides. I minus here also cancels with that I minus there. But let me make sure I speak to that. See this right here and this right here? Well, I minus wasn't generated. It was actually introduced. And then it gets consumed. And then it's regenerated in subsequent reaction. This is your catalyst. A catalyst is a chemical that is introduced early on in the experiment. It's not generated throughout the experiment. It's introduced as part of the ingredients for that reaction. It gets consumed somewhere in the elementary step, but then it's reproduced. So a catalyst is not going to be part of the overall stoichiometry other than the fact that it's needed to provide a different pathway. So this right here is your intermediate, IO minus, because it's produced and then consumed. I minus is your catalyst because it's introduced, consume and produce. Okay, catalyst is going to be introduced, gets consumed, and then it gets produced again. So that's your catalyst. So in terms of this question, what is my intermediate? IO minus. What is my catalyst? I minus. What is my overall stoichiometry? Overall stoichiometry is just H2O2, two of them, going to H2O, two of them, and O2. And then the catalyst, you could actually add the catalyst in here as I minus, and you usually introduce it in the arrow above, indicating that that's the chemical that's being introduced in this particular case. You could also put it here and here, okay? Meaning that it's introduced and then regenerated. But usually what you do is you put it above the arrow, indicating it's a catalyst. So again, the intermediate is equal to, in this case, IO minus. The catalyst is equal to I minus. So let me clear that so you can see my notes on that. Okay. And I would put I minus up here above the arrow, indicating it's a catalyst. You know that enzymes are the biggest group of catalysts out there. Each one of us have enzymes in us, and they catalyze the reaction that occurs in our body. How can you tell that it's a catalyst again? Because it's introduced in the reaction, it gets consumed, and then reproduced, okay? Whereas an intermediate is produced and then gets consumed. So the catalyst shows up on the left first, and then it shows up on the right. An intermediate shows up on the right product and gets consumed on the left. So you just need to be exposed to these different things, because a catalyst is a chemical that, again, is not produced as a reaction and then consumed. It's actually introduced first and then gets consumed and then reproduced. Okay, so let's take a look at this. This right here is an enzyme. It's an enzyme working on a substrate, and this happens to be a catalyst that degrades alcohol. It's called alcohol dehydrogenase. So this is a slow step, the second step, and the question is, what is the rate law for this reaction? Let's double check, make sure the stoichiometry is correct. E plus S goes to ES, where E is the enzyme. It's the catalyst. You can see it's a catalyst right here because it's introduced early on and then it's regenerated. It's regenerated. ES is produced in this first step and then consumed. So E here is your catalyst. ES here is your intermediate. The overall stoichiometry is E plus S producing E plus P. Net would be S going to P. But let's take a look at the rate law. The rate law is going to be equal to K ES. Why? Because this is your slow step. Go with the slow step. But this is an intermediate, so you can't have that. So we need to look at this first reaction, and we can say that K equilibrium for that first reaction is equal to ES. We need to put a bracket on that, indicating it's the molar concentration times E times S. It's products over reactant. The reactants are E and S. Even though E is a catalyst, it's still a reactant that is introduced in the reaction. Okay, so we're going to solve for ES here. ES is equal to K equilibrium E times S, and that's your quantity. Okay, we're going to substitute this for that, and so what we have is K equilibrium E times S. So your overall rate law is K prime E times S. Notice that the catalyst shows up in the rate law, and that's okay, because catalysts can show up in the rate law, but not intermediates, not intermediates. Okay, so let me make sure that you understand that. So this is the rate law for this reaction. Let me just show you that in the steps here. And that's basically what we have right there. So when you guys, we're at a 6 o'clock hour, but work on this problem right here. This is your slow step. And in this particular problem, I make it a little bit more difficult for you because what you need to do is you need to go through two equilibriums. I'll get you started here. First of all, what is the overall stoichiometry? Start canceling out all the intermediates. Chlorine's an intermediate, okay? ClO, CO is an intermediate. HCl is an intermediate. So anything that is produced in reaction and then consumed later on are your intermediates. So here we have HCl, we have Cl, and we have ClCO. And what is a catalyst? Well, your catalyst here is H+. How do I know it's a catalyst? It's introduced early on here and then it's produced in the second step. So your catalyst is H+. That part's, again, you're not doing any complicated math. You're just making sure you understand the concept of intermediate catalysts in this particular exercise. Now, what's the overall stoichiometry? Well, the overall stoichiometry is anything that you didn't cancel. H+ is a catalyst. You've got Cl2 here. You've got CO here. You've got Cl2CO. So that balances the chlorine and carbon, and then you produce an H+ there. Let's remove the H+ and put the H+ right here on top of that arrow, indicating it's a catalyst. Okay, so the catalyst and any of these chemicals in the overall stoichiometry can show up in your rate law. So I'll get you started in the first step. The first step here is the rate determining step, and so that is equal to K, and the rate determining step is that third reaction, this reaction right here. So that's equal to K times ClCO times Cl. The problem with this is that both of these are intermediates. So you have to go back to this second reaction and this first reaction and write the mass action expression, the equilibrium equation, and substitute for that. So try that. Work on that, because basically we're done with this particular chapter. That's kind of good. Kept it to about an hour, but also use that and what we talked about to work on that exercise that I gave you, the second reaction that I gave you, and you have now all the knowledge to work on that. Also, the first question in that exercise, well, one of the questions there is, what is the rate law? And you can figure out the rate law based on those elementary steps that's provided. Okay, so make sure you turn that in by Wednesday, because I would, if you have questions, I want to make sure that I go over that, because that's a telltale, that's a really good exercise, because it brings everything together in terms of the abstract concepts that ties in all the things that we've talked about in kinetics. But that pretty much is kinetics, and we're pretty much done with this chapter.